Yerp, what it do, everybody? Welcome to Modern Physics, the 7-minute summary for Chapter 44, Nuclear Structure. On this channel, a very quick summary. We've gone through relativity, intro to quantum physics, quantum mechanics, atomic physics. I just posted a quick molecules and solids 7-minute summary on my phone. Maybe you guys can enjoy that. Right now, I'm doing it on my computer. And then we got 2 more chapters after that. So let's get right into it. How do I get out of here? Boom. Okay. Maybe I should zoom out a little bit more so we can see what's happening. Nuclear structure. We got 1, 2, 3, 4, 5, 6, 7, 8 sections. Some properties of nuclei, nuclear binding energy, nuclear models, radioactivity, the decay processes, natural radioactivity, nuclear reactions, nuclear magnetic resonance, and magnetic resonance imaging. This is a cool section. Set a timer for 7 minutes.
All right, 7 minutes. Starting now.
Cool. Thank you. The year 1896 marks the birth of nuclear physics when French physicist Antoine-Henri Becquerel discovered radioactivity in uranium compounds. All right, we're going to zoom through because I spent a lot of time on these first little paragraphs. Some properties of nuclei: atomic number Z, neutron number N, mass number A equals Z plus N. Nucleons. Let's check this pitfall prevention. Mass number is not atomic mass. The mass number A should not be confused with the atomic mass. Okay, cool. The nuclide, and check this out. This little symbol here I've seen in periodic tables. X represents the chemical symbol of the element. For example, iron, and they show you some stuff related to periodic tables. Quick quiz, awesome. Charge and mass, going back to E and M. The proton carries a positive charge. All right, we're going to zoom through that too. Atomic mass unit, U, is defined in such a way that the mass of one atom of the isotope C12 is exactly 12U, where 1U is equal to, okay, little conversion between kilograms and U. Little table, very useful. Print this out, put it next to your bedside table, and just look at it before bed. Try not to lose your mind. And it's kind of cute, you know, look at this. Looks pretty cool. Actually, screenshot this and send it to your crush. Should start up some cool conversations. The atomic mass unit, little problem that helps us convert between this. Maybe it's interesting to look at. The size and structure of nuclei. Rutherford scattering experiments, not going to look at that, but let's take a look at this. Because of the Coulomb repulsion between the charge of the same sign, the alpha particle approaches a distance d from the nucleus called the distance of closest approach. We got some equations here, nothing in yellow except this. What is this? Nuclear radius. Damn, how did people figure this out? A nucleus can be modeled as a cluster of tightly packed spheres where each sphere is a nucleon. I'm assuming this little thing here is literally just the radius. So we got A is a constant equal to this in meters. Capital A is the mass number. Cool. So we have the radius of a nucleus there. We got volume and density of a nucleus as an example. Nuclear stability. What does this mean? I see the nuclear force is a very short range, about 2 femtometers, attractive force that acts between all nuclear particles. Okay, we're not going to read that. Nuclear stability, nuclear force, and then a small distance here. Look at this graph. This is the graph that I took a look at in the previous few chapters. It looks like something like this. It's energy here as a function of distance. So if you roll a ball, this ball is going to roll here freely and then fall here and boom. And once it gets stuck in this little like little hill or little valley, it's going to be stuck there and it's not going to move. So this is a way of modeling how, you know, the energy works out such that atoms and stuff settle a specific distance from one another. So very cool graph. Take a look at this one here. The difference in the two curves is due to the large Coulombic repulsion in the case of proton-proton interaction. So here we have a little bump. So if we want to give enough energy to shoot this guy out of here and eject this electron or whatever from this little system, here it's less energy than here because here we have to overcome this extra little bump over here. So that's just some little things I'm thinking about here. Let's see if I missed anything in all of these things. Superposition, line of stability. I'm just looking at little italicized words. This graph looks interesting. Neutron number N, atomic number Z. And here we have one line and another one that kind of go off from each other. Neutron number N. Okay, let's check my timer. 3 minutes. Damn, section 2, brother. Okay, nuclear binding energy. Binding energy of a nucleus. Okay, this looks like crazy, but anyway, we're going to zoom through it. We got binding energy per nucleon, mass number, and we have a couple, like a bunch of different elements. We got nickel, we got iron, nitrogen, whatever, all those stuff. Hydrogen over here is at the bottom. I guess it goes up as you get heavier. 2 minutes 40 seconds on the timer. Section 3, nuclear models. The liquid drop model. Okay, we can take a look at the liquid drop model. I'm not going to spend much time on the 7-minute summary here. We got another equation here. Semi-empirical binding energy formula. All right. Applying the semi-empirical binding energy formula. Okay, so we learn an equation and then we apply it to a problem. Very useful to know. The shell model, we have another number. We have magic numbers here. Interesting. Magic numbers, not sure what they're used for. We got the shell model, independent particle model. Okay, so I guess different models. Maria Geopert-Mayer. Geopert-Mayer, I hope I'm not butchering this, German scientist. Born and educated in Germany, she is known best for her development of the shell model, independent particle model, and the nucleus. Published in 1950. 1950 is fairly recent, like about 60 years ago, 70 years ago. Similar model was simultaneously developed by Hans Jensen and another German scientist. Jensen was awarded the Nobel Prize in 1963 for their extraordinary work in understanding the structure of nuclei, or nucleus. Interesting. Then we got an entire section on radioactivity. If this section confuses you or this word radioactivity scares you, take a look at this. They'll probably explain it a lot. We got the queen herself, Marie Curie, another giant in this field, but I don't got too much time to look at this section. We got an interesting looking equation here, the decay constant lambda. So talking about decay and like radioactive substances and stuff like that. 1 minute on the timer. We got some other equations that look interesting. I know this is a decay parameter, so this is what gets you this little decay thing. We got some other stuff, more decay type equations. Half-life, you may have heard of that video game. We got Curie here, which is actually a unit. That's crazy. The Curie. Really cool, having a unit named after yourself. 38 seconds. How many nuclei are left? Activity of carbon. Radioactive isotope of iodine. The decay processes. Okay, alpha decay. Spontaneous decay, disintegration. 24 seconds left. Chemical and nuclear information. Send this to your crush as well. This is a great way of getting some conversation started. Send them these things. This entire picture in HD quality. The energy liberated, 10 seconds. Oh man, beta decay. Sorry guys, I can't go through this in time. Electron capture. Carbon dating, the age of the Iceman. Radioactive dating. Gamma decay. Damn, my timer. And I never finish in time. Natural radioactivity, a whole section left. A whole other section, nuclear reactions. Maybe there's another one. Nuclear magnetic resonance. I really wanted to get to this. This is super interesting. I remember when I first learned about this, I Wikipedia searched, how does nuclear magnetic resonance work? I straight up lost my mind. This is a really interesting concept. This is that big machine they put people in to see like all the little intricacies of your body. This can measure like really, really fine-tuned stuff. It's not like an X-ray which can only see bones. This can see a lot of other crazy stuff. So anyway, we got some quantum mechanical looking thing, nuclear magneton. They kind of explain here how nuclear, here's the picture I'm talking about. You can see like MRIs of brains and stuff, super crazy. Color enhanced MRI scan of a human brain showing a tumor in white. Super sad, but you know, insane that we've come this far just by studying some physics. So the summary. All right, I'll actually leave this summary here for you guys because I don't want to spend too much time on this section, but I did want to look into my bookmarks really quick. So let's take a look here. All the sections here, what we just went through was nuclear structure. I know I go through these super fast. I'm trying my best to give as much kind of information here, but it is a lot of content. So you got to just learn as fast as you can. Don't worry about mastering everything here. Anyway, we got 2 sections left, and then that is it. So we got 1, 2, 3, 4, 5, 6, 7, 8 chapters. I feel like the bulk of the problems for a final exam would be relativity, quantum mechanics, and maybe some stuff here, particle physics and cosmology, which are very interesting. All these chapters are interesting. We just don't have a lot of time to cover them. I'm going to try to post as many videos as possible. Thank you guys as always for watching. Let me know in the comments down below if you find any of this interesting and if you have any questions or if you have any recommendations of what I can change to help you guys better. And thanks for watching. Peace out.